Hello, everyone, and thank you very much for joining. I am Maria Liapopoulou. I am the chair of the Second Young Members Subcommittee, and today I have the pleasure of welcoming you to our lunchtime webinar on computational fluid dynamics applications for fluid structure interactions. This talk is co-organized by the Second Young Members Subcommittee and the Bath and Bristol Young Members Panel of the Institution of Mechanical Engineers. Let me firstly start with some basic housekeeping rules. Please keep your video cameras off and your microphones on mute for the duration of the presentation. I would like to invite the speaker to keep their video cameras off on if possible. After the end of the presentation, we will have time for a Q&A session, but please feel free to type any questions you may have in the meantime in the chat. And please also note that this webinar is being recorded and will be uploaded on our second YouTube channel. And therefore, by dialing into today's event, you agree that any views or information you share will be made public. Now, a quick announcement from our second talks. This year, our second talks team has launched a new initiative on first steps in civil engineering dynamics. This will be a series of episodes where our goal is to foster an open discussion about the transition from the university to the professional world within civil engineering. And we will be exploring the day-to-day responsibilities of young civil engineers, as well as the journey to obtain professional qualifications. The first episode of this series is now available. Ludovica Pieroni from UCL interviews Daniel Gilmore from Sellafield. So if you are interested in learning more about the work of Daniel as a structural engineer at Sellafield, please check out our episodes. You can find the links for Spotify and YouTube on our second website. And I would like to also thank the rest of the members of our second talks for their valuable contribution to making this possible, including Philip Zinkiewicz from AtkinsRéalis, Hang Lee from AtkinsRéalis, Ziad Khalil from Imperial College London, and Evangelos Sifadidis from Holtec Britain. So now I would like to ask Montse to introduce the Bristol and Bath Young Members Panel from the Institution of Mechanical Engineers.
Hello, everyone.
Can you
hear me?
Okay. Yes, perfect.
Okay. So yeah, welcome everyone. I think it's going to be an interesting session. We are really grateful to be part of this collaboration. We've never collaborated with the civil engineering institution before, so we are up for it. We have a couple of people in the call, but I am the chair of this panel, so I'll present myself. So who we are a group of engineers, like young professionals, either working towards professional registration or we recently achieved it. And what we do is actually really varied. We are having a social this evening, but we are having a couple of lectures in the following 2 weeks. We do site tours, we do networking events, we do things with universities like CV workshops, mentoring, lots of interesting things, and also really fun way to connect with other engineers in the area and companies and find out many interesting opportunities. So everyone is really welcome to join us. We are a group of 33 at the moment, so it's quite big, the panel at the moment, let's say. We just recently launched our Instagram account, but we have a LinkedIn account, you have it there. So anything, let me know if you're interested to join us. Thank you.
Perfect. Thanks a lot, Montse. And now let me introduce our speaker, C. Nolan. C is a CFD engineer in the advanced technology team in AtkinsRéalis, working in a significant amount of interdisciplinary studies within the last 2 years. C regularly performs hydrodynamics, aerodynamics, and thermodynamics analysis, assisting design engineers within a variety of sectors, including buildings, transport, infrastructure, and nuclear markets, among others. So this really highlights the vast range of CFD applications throughout engineering. Prior to this role, she completed a PhD in aerospace engineering at the University of Glasgow, which involved CFD experiments at the National Wind Tunnel facility. Without further delay, I will now hand over to C.
Thank you very much. Yeah, thank you for that introduction. Thank you everyone for coming along to listen as well. Yeah, as Maria said, I'm going to be talking about computational fluid dynamics, and we're going to sort of be touching upon some applications in fluid structure interactions. So yeah, I'm going to start off. I'm going to give a brief introduction about myself, and then an introduction to CFD. Then we're going to look at a case study, and then have some questions at the end. So I'm C. I work for AtkinsRéalis in Glasgow. AtkinsRéalis is an engineering consultancy with offices all over the globe. Basically, we're one of those consultancies that has one of everything. So if it's a type of engineering, it's very likely that somewhere there is a team that specializes in that engineering. This is great for me as a CFD engineer. A lot of my job is sort of coming in and helping out with design engineers on whatever they're working on, and it gives me lots of opportunities to work on different projects and work in lots of different disciplines, which I like a lot. So I got my master's from the University of Strathclyde. I then moved across town to the University of Glasgow, where I did my PhD in aerospace engineering. This was a combination of experimental testing and CFD. So the experimental testing was part of the National Wind Tunnel facility, which was like a UK fund to try and bring a bunch of existing test facilities up to sort of an international standard. So there was lots of new high-tech equipment, which was really fun to get to work with. And then a lot of the additional work that I did was sort of CFD, looking at ground vehicles and sort of interactions between vehicles, looking to understand the aerodynamics and then implement some flow control to see if I can improve it. So once I finished that, I then joined the CFD team within Atkins. So we are spread across a few offices in the UK. And again, this is really helpful to, it allows us to sort of talk to engineers in lots of different disciplines and allows us to work on lots of different types of projects. And yeah, I've been doing that for a couple of years now. So I'm now going to go on to introduce, talk a little bit about what CFD actually is, and some of the motivations and technical considerations that go into building a CFD project. I don't know what level everybody's knowledge of CFD is, so I apologize if this is too simple or if I'm going over stuff that you already know, but we're going to crack on through it anyway. So what is CFD? CFD obviously stands for computational fluid dynamics. That basically means simulating the physics of fluids. This normally means solving the Navier-Stokes equations. There's lots of other equations and physics that can be solved in CFD, but primarily it's the Navier-Stokes equations, which are classically unsolvable analytically. So instead we use like a computational process where we're iterating to get towards the correct result. And this uses sort of discretized domains, so using finite volume approximation, which is quite similar to how like the finite element analysis works with their finite approximations and things, and using an iterative process and making sure that sort of you're converging on the correct result. So some of the motivations for CFD, obviously we can use it for lots of different applications, normally in project design or safety assessments or performance assessments, or looking at ways to optimize different designs. One of the things that we find works best for CFD is when we come in at an early stage in the concept phase. So looking at making a design more efficient or perform better, or maybe highlighting some of the weaknesses in the design or providing some sort of remediation to the current design to improve its performance. But that obviously does require either the client or the engineering team that we're working with to have very clear definition of what performance criteria they're trying to meet. So sometimes this comes from like your standards. It needs to meet the standard for it to pass. And sometimes it's a bit more complicated. Sometimes at the early phase, the client isn't really sure exactly what they mean when they say they want it to perform well. So part of our job is trying to help the client understand what they can expect from the CFD experiment, what sort of data output they'll be getting, and what criteria they're hoping to try and achieve in that. One of the big drawbacks of CFD as well is understanding the uncertainties involved. Obviously, we're running these simulations and we get some results, but the results, we never know exactly how accurate they are. So a lot of our work goes into designing the simulation and looking at all of our different inputs and understanding what the effect change in different inputs has on the final result. And again, it's really important to understand what our output is going to be at that phase so that we can see, okay, if we change the time step, if we change the physics models, what effect does that have on our specific output that we're concerned on? And that allows us to give more robust simulations without having to do a full experimental campaign to validate all of our simulations. On top of that, we also use commercial software. So all of there's commercial software that we use at AtkinsRéalis is StarCCM+. But obviously, there's lots of other software vendors out there. And a lot of the commercial software is backed by experimental testing. So all the physics models that they're implementing have been tested on other things. And that adds an additional layer of robustness into whatever project we're working on. So when we do start a project, there's a bunch of technical considerations that we need to think about. The first one, obviously the main one, is what physics are involved in the problem. So as I said earlier, there's so many different types of physics models that can be applied to modern CFD softwares. And if we turned all of them on, it might give you a more accurate result, but what's actually going to happen is it's just the whole solution is just going to grind to a halt. It's not feasible to do every single physics model all at the same time. So at the early stages, we need to identify what are the main physics that are going to be influencing the problem that we're working on. So is it a heat transfer problem? Is it a buoyancy problem? You know, is it non-Newtonian fluids? Is it multi-phase? Things like that. And understanding which ones are the important ones and which ones we can ignore. Following this, we then move on to the geometry. And again, it's about understanding the problem and understanding what things are important. One thing that I think isn't always fully appreciated is that we're not simulating the whole part. So if we were given in this example, we have a pipe. We're not actually simulating the pipe at all. We don't look at the bolts. We don't look at the flanges. We're looking at sort of the volume inside the pipe. So it's almost like an inverse of the part that we're looking at. So we take like a volume extract of where the flow is going to be, and that becomes our solid that we would then discretize and analyze. In the same way that if we were looking at a road vehicle, say, we would make a big box, which would be our air, and then we would cut the vehicle out of that box, and you would be left with this sort of inverse, like a box with a car-shaped hole in it, and then you would simulate the flow over that. So the solid geometry that we're using is actually the fluid, rather than, you know, the structure that would be simulated. And again, having a good understanding of what the client wants as an output is very helpful in this stage, to understand what detail is going to be relevant to the solution. So, you know, looking at surface roughnesses and things like that. And for this example, we're able to implement some symmetry. So obviously the pipe's symmetrical, so that allows us to cut down on some of the computational complexity that's going on. And then one of our final technical considerations at the early stages is the mesh. So as I've touched on before, we have to discretize the domains. That means chopping it up into either cubes or polyhedrons or kind of whatever shape you want, really. And what we find is as you make the cells smaller, you're able to better resolve the gradients. So if that's a pressure gradient or a velocity gradient or a temperature gradient or whatever it is that you're trying to solve. However, it's not feasible to have tiny cells everywhere because, again, that's going to really increase your computational cost. It's not unusual for a solve to be 6 to 10 hours. These aren't quick things that get turned around in a matter of minutes. So it's really important to focus the computational effort around the bits that are important. So again, this goes back to where having a really clearly defined scope and a real focus on what the output needs to be at an early stage allows you to better target your computational resource to exactly what the problem is going to be. And again, we do a lot of testing on this, so we would often do mesh dependency studies where you're looking at what's the minimum cell size required to resolve this gradient correctly. So what we tend to try and show is that if we take a coarse cell and then we slowly make that cell smaller and smaller, so we make the mesh finer and finer and focusing the mesh on the important regions, we want to see that the solution sort of converges onto a set solution, and then it becomes independent of what the mesh is doing. And that's the best scenario, is that you have a completely independent answer to whatever mesh you're putting on. So that's kind of an introduction to some of the technical considerations that when we first start a CFD study, we think about. I'm now going to move on to a short case study. So the case study that we're looking at, that I'm going to talk through, is a pressurized sphere. So here we have a pressurized sphere with a small hole in it that allows that air to vent out, and then it's going to be interfacing with a simple like L-shaped plate. And what we're trying to understand here is how quickly does the pressure leave the sphere? So what's the decay, what's the depressurization like from that sphere? And then what's the maximum displacement in the plate? Well, obviously there's a lot of complex physics going on in this scenario. So we have compressed air, how that expands out into the surrounding environment, and we also have this fluid structure interaction. So how do we make sure that the fluid is properly interfacing with the structure? Now, when we're building this sort of investigation, we know that there's going to be a lot of different things that we want to try, different physics models, different time steps, different meshes, whatever. So it's important to have some sort of datum that we can measure all of these against. So ideally, in an ideal world, you would have experimental results either from a paper or from some physical testing that had already happened at the site or whatever it is that you're working on, that you can then compare some of your prelim simulations to and fine-tune all of these settings to give you the most accurate result. More often than not, however, we don't have that luxury. Often whatever it is that's being tested, the design or whatever hasn't been built yet, so we can't do any physical testing on that. And the whole purpose of CFD is to try and give you a more cost-efficient solution to just making an experimental test campaign. And not only is it more cost-efficient, but it's also more time-efficient. Experimental test campaigns take a long time to design and set up, and finding the right test houses and things can be challenging. So if that were the case, again, we would just go back to trying to define what the scope is and understand the differences between all the settings, and hopefully find something that provides a reasonably robust solution. In this case, however, we do have a validation paper. So the paper that we're going to be using is from the 1970s. It was a NASA paper by Esparza and Baker. So in this case, they used glass spheres and they refilled them with pressurized gas. They then allowed that gas to cool back to room temperature. And then they were using a pneumatic cylinder to smash this gas. And then you can see they have two pressure probes here, set different distances from the gas. And you can see as the compressed air expands out, measures the pressure like transiently measures the pressure. So the specific case that we're going to look at is compressed air. So it was a 51 millimeter sphere of glass. That's internal diameter at 52.5 atmospheres. And the two measurement locations were 140 millimeters and 165 millimeters. And these are to measure the blast wave as it propagates out of the sphere. So we can see here we've sort of digitized these two pressure traces. So on the x-axis we have time in milliseconds, and on the y-axis we have pressure in psi on this one. So what we see is that I also actually, sorry to note, the scale is different on these two. So this peak looks like it's higher for the second probe that's further away, but actually it's at a lower scale. So this is the higher value and this is lower. So what we see is after the sphere is broken, you get this initial big spike in pressure. Then you get this slow decay into a negative phase and then a second spike in pressure. And again, when you're slightly further away, it's the same, but the maximum pressures, the peaks are a little bit less. So looking at this, one of the things that stands out to me, first of all, is that this change in pressure for the primary wave is very steep. So we're going to have to capture a very, very sharp gradient. And for me, that means small cells. So to capture these steep gradients, you need lots of small cells to get a good resolution. And that's going to be a challenge, because if we have lots of small cells everywhere in the domain that we're trying to simulate, the simulation is going to be very big very quickly. So I was already aware coming into this that meshing was going to be one of the main challenges in the initial setup, at least. Because as I said, the pressure wave is very thin, and it's not practical to have that cell size everywhere. Luckily, CFD, or our CFD software that we're using, StarCCM at least, has some very clever meshing tools. So one of the things that we were able to employ, sorry, one of the things that we were able to do was introduce what's called an adaptive mesh. So here we can look at a certain scalar, and you can say, okay, if it's above this, or if it's between this range, or if it's below this range, or whatever you want, I would like you to add more cells or course some more cells. And this can be done every time step, or it can be done every 5 time steps, or whatever. It's quite a flexible tool that allows you to track things that are moving through the domain without having cells everywhere. Because obviously we can't have static refinements in this either, because the pressure wave is moving through the domain. So two of the main ones that came to my mind, at least when looking at this, were density gradients and pressure gradients. So obviously, as this wave propagates out, we're going to be getting a steep pressure or density gradient. In this case, the density gradient on the left here, we saw a lot of additional noise in the center of the sphere. Now, I think depending on what we were interested in, maybe we would want to resolve all of this additional, these density gradients close to the sphere. But for our purpose, we're wanting to look at this wave as it strikes a plate. So the impulse of that wave on a plate. So we really just want to be tracking the primary wave and the secondary wave. So pressure gradient gave us a much better sort of resolution of what is important for our study. And by no means is this one method is good for all things. It's very problem specific. But then on the right here, we can see an example of how the mesh refines around the primary wave and around the secondary wave, but kind of coarsens up everywhere else, where the flow is not really moving at all. So once we've got the meshing sorted out, we were also able to test a bunch of other things. So looking at turbulence model and solver precision and our gas assumptions, spatial temporal schemes, time step dependencies. Obviously, we looked at mesh dependency, all these things. And we were able to work out which ones are the most appropriate. And I'm deliberately not going into too much detail on the exact setup that we used, because I think it's really important that all of these inputs are very problem specific. I don't want people to come away from this saying, oh, if I want to model compressed gas expansion, these are the things that I should be using to set up. It's really important to target all of your input parameters to your specific problem. And we should always be doing these dependency assessments for whatever project it is we're working on. So when we ran the simulation, we were then able to see plot the pressure traces over the experimental data. And obviously we saw the timing. So we've got, again here, we've got time on the x-axis and pressure on the y-axis. And the black and gray lines are the experimental results. So the black line is node 1 and the dashed line is node 2. And then the blue lines are simulated results, again, the thick line being node 1 and the dashed line being node 2. And what we see is that the timing's quite good. The impulse on the first node occurs at roughly the same time. The impulse on the second node, not quite as close, but reasonably accurate again. But the obvious discrepancy here is the peaks were drastically overestimating the peak pressure. Now, we then have to go and think about the experimental method and what they've actually done. So I went back and I looked, and the pressure sensors that they were using could read up to 3.5 megapascals, so there's no issues there. They definitely had the ability to measure the higher pressures. But then looked at the sampling rate, and they were sampling every 6 microseconds, whereas we were sampling every 0.1 microseconds, and that is quite a big difference. And I think that there's a reasonable likelihood that their sampling rate in the experiment wasn't high enough to capture that peak. And we were quite happy with our simulation that we were capturing a real peak pressure. And this by no means means that it's me saying that the experiment is rubbish, because NASA are a very reputable publisher, and the experiments that we're doing will have been conducted properly. But I think it's more highlighting that it's important to understand exactly what the limitations of all of the methods are, the simulation methods and the experimental methods, to sort of give you a more informed decision when you're making these decisions on how to set up simulations. And yeah, I think that this setup we were fairly happy with what we were able to achieve here. One of the other drawbacks that you could see in the experimental work is, of course, they have these glass spheres that they're hand blowing, so the glass spheres might not have been perfect spheres, whereas we are simulating a perfect environment. And additionally, in our simulations, we have these spheres which has like a solid baffle around, and then at the flick of a switch, we can turn that into an internal interface, and that allows the gas to freely expand. Whereas in the experiment, they have this glass that's getting accelerated, which is again taking energy out of the system. So there's a lot of reasons why the results could be slightly different. And it's just important to understand these and be aware of these. So now we're going to move on and increase the complexity of our simulation. Now that we have this strong foundation simulation based on experimental results, we're going to step up the complexity slightly. So now, instead of letting the gas expand freely, we're going to make a solid wall around the outside and have just a small hole for it to escape through. So our vent here was 10 millimeters by 10 millimeters squared. And we added an additional node in just slightly off plane to try and capture any of the pressure waves outside of that. So again, here we see the pressure expanding, and as we saw previously, you see a big peak as that primary wave hits each node. It actually reaches node 3 slightly earlier than node 2 because it's slightly closer radially. But then what we don't see is the decay that we saw before with the free expanding case. We see this sort of much more unsteady oscillation in the pressure. And what we actually ended up simulating was something close to an underexpanded jet, where you get a series of Mach disks forming that slowly move as the pressure inside the sphere reduces. They slowly move, and we're measuring the pressure at fixed nodes. So as these Mach disks move through the nodes, you get this unsteady pressure at the specific points. We're also able to measure the rate of decay inside the depressurization inside the sphere. But again, reasonably happy with how these results were looking. So it's again time to increase the complexity once more. So now we're introducing the plate. So here we're adding this L-shaped plate. It's 3 millimeters thick steel, and we had it fixed around the outer edges, all the free edges. So obviously it's quite a heavily constrained plate. We're not expecting to see a lot of deflection. And for that reason, we used what's called one-way coupling. So that essentially allows the fluid to impart forces and pressures onto the plate, but it doesn't then, the deflection of the plate doesn't then influence the the fluid. So you don't see, if the plate's oscillating or whatever, that doesn't induce oscillations in the flow. That is possible in the solver, but we weren't expecting, for the short impulse pressures that we're measuring and the stiffness in the plate, we're not expecting to see that. So this is one of the assumptions that we made where we set it to one-way coupling. The mesh here was relatively coarse. Our primary focus here is looking at the displacement in the plate. Obviously, the maximum stress is going to be around the fixed edges. So to capture that, you need very small cells. But because we're just focused on the displacement, we were able to get away with a slightly coarser mesh. So when we ran this, again, we'll see the first impulse and pressure comes very early on at node 2. And then you see a small dip, and then it comes back again as it reflects, as that primary wave reflects off the plate and then re-hits the node. So we can see the first wave sort of hits the plate at around 75 microseconds. You then see the primary pressure wave at nodes 1 and 3 comes at the same time, because they're equidistant from the vent. But at node 3, you see this second peak that comes shortly after the first. And again, this is as the flow oscillates around this corner, it gets concentrated in on node 3. So you get this second peak, which is like the reflections going on. We're also able to measure the pressures and temperatures inside the sphere. So again, we put a node in the center. And one of the interesting things that you see here is that the pressure stays constant for, about 100 microseconds. And that's actually as the simulation starts, and the sphere obviously starts as fully pressurized, and then you have this vent, and it actually takes a while for that wave to propagate back into the sphere. So you don't see any change in the center of the sphere for a short time. And then as it decays, you see this unsteady decay, and that is again because that pressure wave is bouncing around inside the sphere. So it's not a nice smooth decay that you might expect for a vessel that's like venting this pressurized air. And again, moving on to look at the plate. So the maximum force in the plate's in the Z direction, which is to be expected because that's the direction of the vent. We can see the maximum displacement is happening in the middle, but the maximum displacement happens at around 250 microseconds, which is quite a significant time after the initial impulse. So it's quite a delayed response in that. And the maximum displacement is around 0.3 millimeters. So again, it's not going to be enough to have a huge influence on the fluid. So again, this gives us confidence that our assumption that we can use one-way coupling is acceptable. And we can see it decays. Because we're looking at a magnitude on the whole plate, you don't see the sort of the rebound as much. But yeah, it's sort of as it passes through zero, you see the deflection elsewhere sort of picks up. So it's the displacement chart doesn't necessarily look exactly how you'd expect it to. But we were able to capture the peak. And then with the stress, again, it wasn't the primary concern of the study, but able to capture the peak, the stresses. And you can see they're very noisy. And again, this is just because of the resolution of the mesh that we went with, because the stresses are around the edges and the cells around the edges aren't fine enough to properly capture that. But again, we can use this to sort of justify that our setup is correct and that the peak stresses are where we would expect to see them. So the outcomes of the study, so we've sort of gone through and discussed how to iteratively build up a simulation, building upon a strong foundation from a validation case. We've shown how to implement some fluid structure interactions and how that's able to work. And we were able to analyze the pressures as they reduce from this venting sphere. Now, this can be applied to lots of different cases. It can be used to quantify loads on a new structure. It can be used as a safety case for an existing design, or if we forget about the structural side for a second, we could just use it to solely look at the fluid pressures and how different shapes can concentrate pressure. So there's lots of different applications for even just a simple case like this. And there's lots of applications for CFD beyond this as well. So I hope that was somewhat interesting and maybe something new. Thank you very much for listening. I think I can open up for any questions if there are any.
Thank you very much, C, for a very nice presentation. I would like to ask the audience if you have any questions, please feel free to type in the chat or unmute yourself and ask. So, Evangelos?
Yeah, I just have a question. Thanks, Maria. Thanks a lot, C, for this very insightful presentation. I don't have particularly good knowledge on CFD, so I thought that was really useful for my knowledge. I just have a question about the deformations and the stresses you were investigating in your plate. So I was wondering, are there any kind of acceptance criteria that you follow, like any code standards that you say we shouldn't exceed these prescribed limits, for example?
Yeah, so I know for structures, there's lots of really useful codes and guidance and things. For the CFD side, there's a lot less, which is interesting. I think because it's such a versatile tool and there's so many different things that you can use it for, it's very hard to pin down any like specific setup things that you should always do. I know that for Rail, there is a standard for CFD, and in other applications, you sometimes get standards for wind tunnel testing and things. But yeah, there's no like British standard or EU guidance or anything like that on any like general CFD best practice and things. So yeah, it's I guess a lot more open to interpretation. I think it can be somewhat risky having that because it leaves it open for someone to just jump on the tool and push some buttons and get an answer and be like, oh, that's great, we've got an answer. And I think there's a lot of thought that has to go into it about really understanding the problem and what physics are important, and a lot of engineering judgment that has to go in, which can be difficult to express to people that aren't super familiar with the topic, I guess.
Okay, thank you.
There is a question in the chat from Daniel James Murdo. What were the boundary conditions used in the two cases?
Yeah, so we were using, let's see, so for the sphere, we were just using internal interfaces and baffle interfaces. So these are like surfaces, so they're infinitesimally thin, I guess. So the internal interface essentially works as like it's just open, and then a baffle interface you can works as a wall. And then for the interfaces here, it was all just fixed edges and like a solid wall interface. And then on the external boundary, there's some interesting things with obviously we use just like a pressure outlet on the external boundary, which essentially just allows any pressure to leave the domain. But you can use non-reflecting pressure outlets. So that then says like if the pressure leaves, it doesn't like if the pressure wave leaves, it doesn't then bounce back in from the far end.
Great.
So,
yeah. Another question from Ashraf Nayel. For the validation example, how many trials you've carried out until you came to the final one? And how long did it take to solve it?
a lot of trialing. So I think we ended up around 25, 30 different simulations to test out all the variables. To begin with, we tried to keep the simulations quite short, the solve time on them. So we're sticking to around 3 or 4 hours. For those cases, as we increase the complexity, obviously the solve time also increases. So for the final case where we were looking at the full fluid structure interaction, we were getting up towards like 15, 20 hours for the solve. Obviously, yeah, it's like it's a balance, right? It's like the level of complexity that you put in then dictates the solve time. So it is trying to find that balance where you're putting in enough complexity to accurately answer the question without having it take so long that the client is like unacceptably long for the client, basically. So we try and keep them to around half a day at max most of the time.
Okay, great. Just to follow up on this, what kind of computational resources do you need to run these analyses? Do you have access to HPC or
we're not just running these on our laptops. Yeah, so we have HPCs that we can remote into them and run them. So our current license allows us to go up to 1,000 cores.
Okay.
Yes. And we can also use, depending on the client and the work, we can also use cloud compute as well. So Star CCM has their own cloud compute servers that we're able to use.
Okay, great. So another question from Mariana Edward. Is this method used to analyze heat loss in building?
So this specific method, no, but you can definitely use CFD to analyze heat losses. It's one of the main things that essentially there's like 3 main things that it's used for: is aerodynamics, hydrodynamics, and thermodynamics. So thermodynamics, the third one, is sort of heat transfer mechanisms. So yeah, you could definitely use it to analyze heat losses through a building. You can look at heat transfer through solids. So you could sort of have your building, and then you could have all your walls and your windows and things and apply heat transfer coefficients through them. And then you can also model the fluid phase where you have your convection currents and things like that, and radiation and things. So yeah, it's slightly different physics to what I was talking about in this presentation, but yeah, it's definitely doable within CFD in general.
Great. Then Prastanta Rai has written, thank you for the presentation. How would you know the size of mesh to take into consideration that would be good enough for the analysis?
Yeah, so when you start, you don't always know what size is going to be good enough. You often have to do this iterative process where you start with a size that you think looks about right, and then it sounds very hand wavy. You start with the size that feels about right. So if you're looking at a structure which is 1 meter tall, for example, you say, okay, I would like 50 cells over that meter or whatever, and that sort of defines your initial cell size. But then you have to do this iterative process where you start very coarse, and then you slowly make the cells smaller and smaller and smaller until you find that the result's no longer changing. So what we tend to do with that is, if you've doubled the number of cells in the mesh and you've not changed the result by a significant amount, then that's considered independent of mesh at that point, and then that's where you can stop. So this is something that we have to do on all of our projects, is to show mesh independence. And we don't always quote that back to the client, but for best practice on our end, this is something that we're always looking at to make sure that our solution is independent of mesh.
Okay, and then Andrew Lasks is asking, is there a preferred mesh shape? For example, grid or triangles or polygons? Or is it very much a case-by-case basis?
It's kind of both. So it's definitely case by case, without a doubt. But it's also like engineer by engineer. Because I definitely prefer cubes, so hexahedral meshing. I like the structure that it provides. It has its benefits and its downfalls. It's very quick to make these meshes. So if you're having meshes with millions of cells, a structured mesh is going to be quicker to create. But a poly mesh, if you have these complex structures with lots of bends and twists that squares don't or cubes don't fill very nicely, using a polyhedral mesh fills the space a little bit better, and so can provide better results. But yeah, so it's case by case, but also a little bit up to what you want.
And one more question from Evangelos Fadidis. What is the error percentage that you aim to achieve to decide that the mesh has been optimized? Would it be like 5% or less?
Yeah, normally we're looking for less than 5%. Normally it's 1 or 2%. So if the result isn't changing by more than a couple of percent, then we'll say yeah, that's independent. What we normally plot it, so you would have number of cells versus whatever variable it is that you're looking at, and it's normally quite easy to see when it's converged. Yeah, it's normally a few percent.
Okay. A question from me. You mentioned at the beginning how important it is to decide at the early stage with the clients the level of accuracy that would be needed. So I was wondering, how do you communicate the CFD results and parameters that may be important to clients who may not have the technical background for these specific applications?
Yeah, it can be difficult. Obviously, the clients that we're talking to, most of the time are engineers. So normally we're helping engineers with their design. Sometimes it's people in transport industry or whatever who sit on like city councils and things. But most of the time we're delivering these to engineers. But that aren't experts in fluids. So it can be difficult to show the assumptions that we've made without getting too technical. But we try and give an indication of what assumptions have been made, what that means for the result, and try and give them a very controlled, like, these results can be used for this application. However, if you were to change the design in this way, or change the operation of whatever it is in this way, then that is going to have an effect on the assumptions that we've made, and like the results will no longer hold true. But it can be a challenge. I think it's just about having open communications with the client on their side so that they understand the process a bit better and what decisions are being made.
Great. Okay, is there any other question from the audience? Yes, Andreas?
Yeah, I'd like to ask a question. So there is the fluid dynamics solver, the solver that takes care of the fluid domain, and I don't pretend to understand that. But then you also, in the case you had there, you had a plate, which is a solid region. Is that the solver for that? Is that incorporated in the same software, or is it a different piece of software that you're using?
So it's all incorporated into the same one. So most commercial softwares now have the ability to do at least simple structural solves. It's not going to be as detailed or as accurate as a dedicated solid solver. But yeah, I think StarCCM definitely has the capability. I know ANSYS allows you to sort of take the outputs from your Fluent simulation and import it into ANSYS Mechanical. So I think the commercial software at least is trying to target towards being able to do a bit of everything.
Okay. Yeah,
I think from the other direction as well, I know some of the structural solves are trying to introduce some simple fluids as well to try and capture that.
Okay, no, thank you for that.
Any other questions from the audience? You can either raise your hand or type in the chat. Okay, I don't see any more questions. So with that, I would like to thank our speaker again. Thanks a lot for a very interesting presentation. And we can end the call. Thank you all for attending. Thank you very much.